Okay, good morning. Welcome back to Foundations of Computing. Today we will go through an advanced lecture and I will discuss soon what that is about. But before doing that, I would like to complete the lecture of last time. Last time we discussed exception handling in the second part of the lecture. Didn't quite have the time to go through all the content. So I would like to quickly wrap up on that. And specifically what I want to discuss now is some of the common Python exceptions, which we didn't have the time to go through. So here is a nice list on the slide. And it's important to recognize them to decide when to place one of these exceptions in your except block, right? So to obtain the desired behavior. The first one is this attribute error. In this case, this happens when you're trying to use a method, which is commonly called a method or an attribute, which is associated with an object that doesn't have the particular method or attribute. For example, if you try to call a string method on a number. So let's look at an example of this. So let's say, for example, I have num5, which is clearly an integer, and I try to call on num a method which is lower, which is a method for a string type. In that case, I will get an attribute error. Second kind that we have here on the slide is an index error. This is quite intuitive to understand. We are trying to access an element within one of our iterables which is out of range. So let's go through a very, very quick example of this. This is extremely common. So let's say, for example, I have a list of numbers, I for I in range 0 to 2, and I try to access nums 3. Right? So that is not in the list, so I get an index error or an out of range error. Key error, this has been discussed many times. In this case, what you're trying to do is to use a key in a dictionary that hasn't been defined before, and therefore you get a key error. And I will just go quickly on this, past this. Name error means that you are trying to use a variable that hasn't been declared or hasn't been defined before. For example, again, very, very quickly, if I do print x, I get a name error because x hasn't been defined. Then the next one is a type error, which we were discussing a little bit during the last lecture. Specifically, a type error is raised when you perform an operation on the wrong kind of object. What that means is you're trying to use a method which is not associated with that particular type, and that you get a type error. For example, if I'm trying to do a concatenation of a string with a number, right? So that is the wrong type. 5 is an integer. I cannot use concatenation in this case between the first string and the second element, which is an integer. The value error instead occurs when you pass the right type, okay, but with an inappropriate value. For example, let's say I am trying to, let me make this clear again. I am trying to convert a string to an integer, okay? So I use the int function, and instead of putting a literal for an integer there, I put just a word. All right? In this case, you get a value error. The type inside the function is not wrong. What's wrong is the value. It doesn't make sense. It cannot be converted into an integer. What else there is after that? Well, file not found error is pretty obvious, and we had a go at we discussed it, and we will have a go briefly later after this slide and seeing what is a file not found error. But basically, what you're trying to do is to access a file that it's not, it doesn't exist, or you got the name wrong, and therefore it cannot find that particular file. And the zero division error is one that we have seen last time during the lecture. Okay, excellent. We had also a short exercise here trying to put together what we learned last time on functions as arguments as well as on exception handling. I will go through these a bit more quickly just to point out what are the main places where we are using the functionalities that we have discussed the last time, as we have quite a bit of content to go through today in the advanced lecture. So what we wanted to do here is to write a function to process multiple files which contain product prices, and we want to integrate them into a dictionary. And what we want to do is to showcase how to handle cases where we have files that might be missing or misspelled and prices that might be formatted incorrectly. So how do we do that? Well, first of all, we need to, as usual, to look at our inputs. In this case, our inputs are these three files called the prices 1, 2, and 3, and each one of them has these objects that are already prepared to be integrated in a dictionary, right? So the first word, we can use it as a key, and the second number instead can be used as a value. But there is a case, for example, in prices 2, where we have provided just some characters, which are not numbers, they cannot be converted into numbers, ABC, I'm talking about this one down here specifically, and so we will have to handle that situation. We're trying to convert that from a string into a floating point number. Okay, so I will just have a look with you at the code here that I have reported on the slides. So what we are doing here is to have our files defined here. Actually, let's grab this and put it as it is. In our VS Code. Let's see whether that works. Oh, that's not nice. So, if we start looking at this at the top, while I'm finishing up my indentation thing here, what we notice is that if we wrote the code say, step by step, probably, we would have gotten immediately that if we are iterating over file names, right, and then we are trying to open files, one sensible thing to do is to wrap our open file in a try block to check whether we can actually open the file, meaning that the file name might be misspelled, the file might not exist. We are trying to open it in read mode, not in write mode. So because it's in read mode, the file needs to be existing. It's not going to create a file for you. And therefore, we wrap it into in the try block, and the matching except is file not found error. And then we need to decide what we do given that we haven't found the file. In case we haven't found the file, in this case, we are just printing that the file name, that particular file, with the file name we are using an F string here, was not found. The other possibility is that also something else went wrong. Here we are using this notation of exception in general as E. What that would mean, which is something that we haven't seen, is that the runtime raises an exception. That exception, remember when last lecture I mentioned, every time an exception is raised, Python will create an exception, object. And that exception object is caught by that particular except because it's pretty general. And it will become this variable E, right? And so what that means is that then when I'm printing the error here, we get the name of the exception nicely printed out there, which is very useful. Then the third kind is internal to the loop structure here. And it has to do with the fact that we might be converting a type that is not possible to convert into a float. So we are trying to code up our prices, as we saw from our files there, in floating point numbers, okay? But we had a situation here on prices 2, where banana there had as a second word on the line ABC. That's not going to be able to, Python is not going to be able to convert that into a float, which is going to raise a value error. And that's what we are trying to catch here. Okay? Any questions on this at this point? I might give it a go to run. So here in this, note something, in this, I'm using a list to give the name of the files, so it's just a list of strings. And I have given a file that actually doesn't exist, so we will raise the file not found exception in this particular case. And so if we make this a bit bigger, that should be visible. As you can see, is raising two exceptions in this case. One is coming from the value, which was in prices 2, which was an invalid price. And it's telling me also which one is the entry. And then the second is the file not found error, which is the prices for not found. We are skipping that file. Okay, so this was just a quick example of how to use exception handling actually, not exceptions, how to get exceptions and to handle them. Again, any questions on this? If not, I will jump into the content of the advanced lecture. Okay, seems all good. Okay, so we are now changing gears a bit. So in this lecture, we are going to discuss a bit more in detail objects and features associated with objects that will give you a bit of a deeper understanding of how Python handles objects internally. Specifically, we will look first at Python's object model, specifically for strings, lists, tuples, functions, and dictionaries. Then we will go back and expand a bit on the concepts of mutability, and of course immutability associated with that, how Python manages object identity and references, and finally, we will have a more detailed look at the internal structure of dictionaries, which are some of the most powerful, among the most powerful types that you've seen before, so far in the course, but I'm pretty sure they look pretty mysterious and trying to understand how they achieve, for example, that quick lookup that you can do with dictionaries. So while these are advanced topics, they will definitely help you in becoming more proficient and understanding Python better. This is an advanced lecture, so the content that we'll go through today is not examinable. It will not be part of any of your assessments. Okay, so at the core, Python is an object-oriented language. So the first question to answer is, what is exactly an object in Python? And I know that Kat has already delivered an advanced lecture on this, so I will go briefly through this to remind you a bit of what an object is. So an object is just an entity in Python that holds both data, called attributes, and functions, called methods, that can act on that data. So in practice, an object is an instance of a class, where the class defines the structure and the behavior of that particular object. And here we have an example of a dog class, which you can see there on the code. To define a class, use this keyword class. This provides a template, essentially, for all objects which are of the dog kind. And to define a class, you have to use this init function and provide as the first argument self. Then there are some extra parameters that you use to define your attributes. In this case, a dog is defined by its name and its age. And those are the attributes that we have for the dog class or for a dog object. And then there is a method called bark, again, that has to take self, which is a reference to the object, to an instance of that particular class, although that is an advanced feature, and I'll just put it there. And we can print that, print self, the name here, will give us with an F string, whatever the name of the dog, and print it out. And that's a method specific to this class. Below that, then we define my underscore dog, and that is an object which is of the dog kind, so that is an instance of a dog. Okay, and we can see that we use this particular function, dog, which is a constructor, to build a dog object. Once it's built, we can use the method bark on that particular dog object. Now, every object in Python, whether it's an integer, whether it's a string, or even a list, follows this model. Yes?
I was going to ask, how do you handle like
you have to provide explicit functions in there that define how that conversion is done. And that's what is internally defined for basic types like strings, integers, and floats. And when it doesn't have it, that's when it says, okay, I have here either a value error or a type error, depending on which one it is. So what's interesting about Python is that everything is an object. So even primitive data types, where by primitive I mean very simple data types such as integers and strings, are objects. And they are categorized, objects are categorized based on their type. By type here, we really mean their own class, right? Their identity and their value. The identity of an object is a unique identifier. You might have looked already through this. And in practice is its own memory address. Where is this object in memory? And you can find that out by using this ID function. The type specifies the kind of an object. Here it's not on the slide, but you can actually use the type function to get to the type of, which will return the type of that particular object. And then value. Value here is a bit used in a generic way. Obviously, for an integer, there is one value associated with it, but for many classes, for many kind of objects which are more complicated and more complex, there might be many values. For example, think of a list. Obviously, in a list, there will be multiple values, and so those are the attributes associated with that particular class. We have also looked at the fact that objects are classified into two broad categories, which are mutable and immutable. And simply, immutable objects are the ones that once they're being created, you cannot change the value of that object. If you try to assign a new value to an immutable object, you're going to create a new object. And these are integers, strings, and tuple that we've looked so far, while mutable objects can be changed after the values of mutable objects can be changed after their own creation. Now, this is just a preamble to get to some more interesting features. So let's remember a bit about mutability. Let's say, for example, for tuple. So if I use a tuple here, I define a tuple, say 1, 2, 3. Since a tuple is immutable, if I try to assign the first element of this tuple to something else, I get an error saying, okay, this tuple is immutable. However, things get more interesting where you start nesting mutable data types within immutable data types. What do I mean by that? Let's take this other example where the first element of this tuple is an integer and the second is an empty list. So what will happen if I'm trying to do, for example, trying to append a value, whatever that value could be, let's say, I don't know, hello, to the second element of that tuple. Is it going to work? Yes? Okay, so there is a yes here. Anybody else? Let's try it out. So it is working. Although, and we can print this out. And you can see that this seems a bit of a contradiction, right? Because tuple is an immutable data type, and I might feel that I have changed the tuple. In practice, what I have changed here, it's not the tuple. I've changed only the list. And this has to do on how internally Python sees these objects. So for the time being, of course, what you want to be aware of is that although tuple is immutable, if it has mutable objects in there, I can change those mutable objects. And I will explain why this is the case pretty soon. So we need to understand that, we need to look a bit more into objects' identity in Python, and also how objects are related to references. So every object in Python has a unique identity. We said typically this is implementation dependent, but I haven't found an exception yet. It represents its memory address, and you can get it by using this ID function to retrieve the identity. Now, the identity remains constant for the entire lifetime of the object. So if I have a mutable data type, such as this list here, I can create a list, which is an empty list. I can do ID on this list. I can append an object onto this list. And I can ID again. And the ID is not changed. Okay, so the identity is constant here. Now, when you assign, how does this relate, and why this is important to how Python sees the objects? Well, you can kind of tell from here. Python doesn't really see the object as its content. It sees the object as its memory address. Okay? So when you're really talking about an object in Python, you are talking about a reference to that object. And that is why the ID is not changing, because the address of that object remains unchanged, but its content can change. So let's look into this a bit more concretely. For example, let's say that I define two integers. These are, remember, immutable data types. So int1 to 10,001. And then I can assign int2 to int1, right? And obviously, if I test whether the value of those two objects are the same, I should get true, right? So let's say int1 equals int2, right? All fine so far. That's expected behavior, right? But there is another way to check whether the two objects are actually the same object under the hood. And this is using the is operator. So if I type in int1 is int2, I am actually asking whether under the hood those two variables are actually representing the same object, and I get true. I get true because when I am assigning int1 to int2, what I am actually doing is just saying that int2, in this case, is another reference to the content of the memory cell that represents the value of int1. So I'm just operating on references. And this applies to some of the objects, to some specific objects. In general, of course, you need to be careful with the identity for mutable objects. So in Python, this is a feature of specifically that, we are talking of immutable objects. We assigned int2 to int1. We just get a change of reference. But since the object is immutable, obviously, what's important to realize is that if you reassign int2 to something else, 300, obviously, object 1 hasn't been changed. Right? Why? Because even if int2 was a reference to int1, its own immutable nature says, well, if you reassign this object, I have to create a new one. So in practice, I have created a new object by assigning I've created a new integer by assigning int2 to this new value. And you can check this with the ID as well. Right? So if I do ID of int1 is that, and the ID of int2 is different. Excellent. So for, obviously for mutable data types, how does this work for mutable data types? Well, let's say I define a list, which is an empty list, and then another list, list2, which is an empty list. So if I take the idea of these two, do you think they are going to be the same? Who thinks they are going to be the same? Raise your hands who thinks that the ID of these two lists is going to be the same. Nobody. That's good. So it's not going to be the same, and that's the expected behavior, right, of what you have seen so far. And it is true. So if we do ID of list, we get this ID. And if we do ID of list2, we get a different ID. And importantly, obviously, if we instead do a comparison of the value, we still get true. Now, things, though, get a bit hairy with integers. So what happens now if I take the ID of these two objects? I've done the same thing as for lists, right? What do you think is going to happen? Might
be the same because it's an immutable data.
Well, does it have to do with the mutable data type necessarily? I mean, from a high-level logic perspective, why should treat immutable data types differently from mutable data types for that?
Because it'll change if you add anything to it, I guess. So it's set. One is set as a value. So if two things point to one, then they should have the same ID.
Let's say, for example, let's do another example. Let's do int3 equals 10,001, right? And int4 equals 10,001. Does that change? So let's test this. Okay, let's see whether int1 is int2. So they are the same. Int3 is int4. It's false. What's going on here? Yes?
Is it the way
No, unfortunately. What did you mean by that precisely?
So,
I might have misunderstood.
well, maybe I don't. Maybe I've missed a few lectures, but one would be stored as specifically, 0, 1 in binary,
Mm-hmm.
and that would be given an address in the computer's memory, wouldn't it? Or stored somewhere. And
Yep.
then when you assign int1 to it, that it points it to that address.
Yeah.
And then same thing with int2.
Mm-hmm.
But is there something that when an integer gets too large?
Right. So it has to do with the fact that it's large. It is not related to the binary nature of it, but it is related to size. So what Python does is to cache the value of small immutable types, such as small integers and small strings. Okay? So for small integers, it's saying I have pre-allocated a bunch of small integers, and every time you assign an object to a small integer, I'm going to make it a reference to the same integer. Why? Because when you create objects in Python, when you assign a variable for an immutable data type, you have to create that object. So there is an overhead associated with that. The same for strings. Imagine every time you assign a variable to a new string, you have to create that string. So Python is saying, I want to optimize this. And so I have, for integers, a list of pre-cached integers. And that goes up, I don't know to what, maybe 1,000, I have no idea. And for strings is even more interesting because what it does, so let's say string 1, I think this is the example that we had with Chuck. All right. And string 2, we assign to the same. Formally, these two should be two different objects, right? As they were for lists, but they are not. They are the same. And that's the same thing. Now what it does is say, okay, you have created this small string, and I've seen in the code that there is another variable that wants to use the same content, so I make it point to the same cell in memory. Obviously, if I reassign string 2 here, I'm not going to change string 1, right? Because this is an immutable data type. But if I did this with a list, so if two list variables were pointing to the same place in memory, changing one will change the other. For example, let's say list 1 equals 1, 2, 3, and now I have to do it explicitly, right? I have to say list 1 is list 2. List 2 is list 1. Now, what I have in memory are list 1 and list 2. They point to the same place in memory. And so if I reassign the first element of list 2, what I have done here is to change also list 1. But that is not going to happen for immutable data types. Okay? Is this clear? This is a bit of one of the...
So strings they point to memory.
Yes.
And if immutable, so that means we just throw an error if you change.
No. So instead of giving you an error, what it will do is to create a new object. Okay? So even if the string under the hood would chuck string 1 and string 2 in this moment, they are pointing to the same place in memory. But because the string is immutable, when I reassign string 2 to a new string, it's not going to give me an error is going to create a new object in memory. It's going to take that string 2, and the reference now is pointing to wherever this new set of characters is in memory, while the string 1 has remained unchanged, obviously. So this is really the equivalent, pretty much, of our previous example. Right? And this is because the list is mutable and the string is immutable. Is that clear? Okay, excellent. Let's go through a couple of other things, and then we'll have probably to close. I didn't have as much time as I liked to have. Another very interesting feature of Python, which has to do with this representation of objects as references, is that functions themselves are objects. And what that means is that as any other object, they can be assigned to variables, they can be passed as arguments, and we have seen that during the last lecture. They can be returned from other functions. For example, let's say, well, here we have this example where we are taking the type of print, which is our print function. And as you can see, the type is this built-in function or method, which is a class. So it is an object. Print is an instance of that class. And it has an ID. But what's very interesting here, which we can do live in the coding, is because this is an object, I can take a variable called myPrint and assign it to print. And that would work. And then I can take myPrint and use it as the original function. And obviously that would work also for print, right? Now, where it gets nasty is that you can delete objects, right? So in general, you can delete objects by using the del operator. So I could actually use that, which I'm not going to do, to delete the built-in function print, and then it won't be able to find. Or actually, let's do it just for fun. Oops. Oh, that is because I have reassigned it to myPrint. Well, it's the same here if I do this. Right? So now if I run myPrint on hello, that's not going to work because I have deleted that object. Okay? Another thing that I can do, because of the fact that functions are objects, so let's say maybe whether print is working now. Yeah, it's still working. So what I can do is to take print. It's an object, right? I can assign print to another function. I've assigned it to length, or len is actually the name of the function. So what is going to happen here is that if I do print hello, instead of printing out the string, is going to give me the length of that string. Okay? And this is because these are objects. Of course, you want to be very careful with this. I strongly argue against any cases where you want to take a built-in function and reassigning it to another function or trying to override that particular name. Okay? But it is a bit of a consequence of the fact that, on the other hand, this allows us to use functions as objects and pass them as arguments, which is what we have done during the last lecture, which is a very useful feature. Okay, I'm almost out of time. So we'll try to add this content to the next advanced lecture. But basically, one of the things that I wanted to discuss today, and I will get to the point where I just raise the main issue that I would like you to think about. So let's say we have studied strings, lists, tuples, and dictionaries. And here there is a summary of all the operations, of some of the operations, that we can perform on these objects. We can add items only to lists and dictionaries because they are mutable. You cannot do that with strings and tuple because they are immutable. All the 4 types support indexing. All of them, in a way or another, support lookup. By lookup, I mean I search for an item, okay? And so we use the syntax value in that particular iterable. Only string, lists, and tuple support the slicing for obvious reasons. And then order preserving, what does that mean? If I insert objects in one of these iterable, does it preserve the order of insertion? So for strings, seems pretty obvious, yes. So do lists and tuples maintain the order of insertion? So if I keep adding items, do they maintain the order of insertion? The answer is yes. Dictionaries, what about dictionaries? Do they maintain the order of insertion?
Doesn't matter, because it's assigned to a key.
Right, so a dictionary, the order shouldn't matter that much because we'll see the kind of data structure that is the way it is designed, but it turns out that it's kind of useful, right? Because if I want to loop over the key value pairs, it would be nice if I know that that the data structure is preserving the order of insertion. And so the answer is, it does it, but only from Python 3.7. Before Python 3.7, dictionaries didn't maintain the order of, preserve the order of insertion, which is for the reason that we've just been discussing. We might argue that for these particular data structures, they might be intrinsically unordered. But it's not the case from Python 3.7. And so I want to leave you and close this lecture with some observations that you want to think about. So now that we have seen the operations supported, what is interesting about strings, lists, and tuples is that the indexing is performed in constant time. What does that mean? That means that if my data structure keeps increasing, okay, it still takes the same amount of time to grab an object at a specific index. And that has to do with the internal structure of those objects. Instead, if I do lookups with strings, lists, or tuples, that becomes slower and slower as my object is growing. So if my list gets longer and longer, it's going to take longer and longer to look up for a specific object, for a specific element in that iterable. Why is that? Because you literally have to run essentially a loop and search for that object, looking at all of them in the data structure. So it makes sense, right? So if I have n elements and I keep growing them, then looking up in that data structure gets slower and slower. And in computer science, we say this has linear time complexity, which is that big O notation with order n. In contrast, the same operation, looking up, searching for a specific value given a key in a dictionary, takes constant time. So even if the dictionary grows, that access time is constant. And this is a big advantage of dictionaries. And so you might wonder why this happens, and this is what we'll explore a bit in the next advanced lecture, which I believe will be next Friday, by the way. We will look at the internals of these data structures to understand how to achieve this behavior, which ultimately will result in you knowing when to use one data structure rather than the other. And with that, I will be closing here. Thank you for coming today, and I'll be happy to take any questions.